In the previous chapter, we have started to talk about timers, which is a hardware source or resource in an AVR that we can use it to create larger delays or count events and create loops, timing loops, and so on. And in this chapter, we are going to see something again which is related with the hardware side, which we can generally use in the microcontrollers or in embedded systems for multitasking. Now, we'll talk about interrupts. We'll define what interrupts are, and we'll also compare with the polling, which we have already seen in the previous chapter. Then we'll introduce the interrupt unit in AVR and how we can execute interrupts and external interrupts, the timer interrupts. We'll do some examples. And we'll talk about how the interrupts are prioritized in the AVR. If we have an interrupt, can we create an interrupt inside of an interrupt? Task switching and resource conflict, and also give you an example about the C programming side. Okay, so what is interrupt? Now, think about it this way. Now I'm teaching this course, and let's say we are in the middle of the course or the lecture, and someone just came in and interrupted because there's something urgent and I have to go, for example. Now, what do I need to do is I have to finish my sentence, and then I'll tell you, everyone, that I have to leave and so on. And then I go and serve that, whatever it was urgent. This is a interrupt example. Or maybe you are in the middle of a process that you are doing something, and then you get a exception. So you have to stop doing what you are doing and you have to do something else. This is what interrupt is. Interrupt is an exception, and it's a change of the normal progression or interruption into the normal flow of the program execution. So when we talk about embedded systems, an interrupt is a essentially hardware generated function call, and they can be both internal, external resources. And what it does is interrupt causes a normal program execution to halt. And for that interrupt, we need to have an interrupt service routine. So we have to do something to serve that interrupt, and we have to execute that. So when we are done with the serving that interrupt, we go back to the normal execution and we resume where we have stopped at. We are going to see an example to it. So these are all the definitions given for the interrupt, and ISR is quite important because when you're having it interrupted for the program, you have to define what that interrupt is going to serve. That's why we need interrupt service routine or interrupt handlers in the program. So one thing that we need to be careful, interrupts, they are infrequent events. Like it can be an external button will be pushed, like resetting, or it can be a keystroke, or maybe thousands of clock cycles. When it is counted or when it is reaches that point, it will generate an interrupt. Say, okay, I had 1,000 clock cycles. Let's serve it, or let's send the data to somewhere. Okay, 1 millisecond ticks. Or maybe interrupts can be from, okay, I received the data. Please stop what you are doing and serve this, get this data and do something. Or maybe I have converted analog data into digital, let's store it. So these are similar, quite examples, few examples that we can give how a VR is going to get these interrupts. or from where. So there are different resources that AVR can get these interrupts from, and these are just the examples to it. Now, microcontroller response time to interrupt is very fast. It's around 4 cycles for AVRs. 386 microprocessors, 59 cycles minimum, and 104 cycles maximum. Now, when you think about that, the time is really critical. We can use a polling loop. We have seen polling loop in the previous chapters, chapter in timers. They can be faster, but you have to think about it because in polling, you have to keep checking. If the flag is set, not set, go back, wait and go back, check again, check again, check again. It's holding over there. It's waiting there until it is set. Okay, so these are the examples that we can give for polling, which we already done in the previous chapter as well. Okay, so when we talk about polling versus interrupt, because we can serve several devices while we are doing something else in microcontrollers, and we have to use polling or interrupts. Now, the interrupt method, the device which is going to cause an interrupt, it sends an interrupt signal. Now, when the microcontrollers receive that interrupt signal, it stops whatever it's doing or saves the context somewhere, but we have to tell that. And then it serves that device, for example, timer. Okay, and in order to serve it, we need that ISRs, so interrupt service routine or interrupt handler. And when it is done, it returns back to the original point which was running the normal program, and it carries from there. But in polling, as I already said, the microcontroller continuously monitors the status of the given device. So when the status condition is met, then it performs the service and then returns back to the ordinary routine. But the thing over here is polling uses lots of CPU horsepower, and you have to wait there. You cannot serve anything else. You cannot actually do a multitasking at some point because it's keep checking whether the peripheral is ready or not if it reaches to that point. So interrupts use the CPU only when the work is to be done. So you can just serve it and return back. And polling or the polling code is messy and unstructured. You have to create loops, and you might need to create multiple calls and to check if the peripheral is ready or not. And we have to keep it over there. But on the other hand, interrupt service routines can concentrate all peripheral code in one place, which we call it encapsulation. And poll code leads to variable latency in servicing the peripherals, and timing can vary depending on taken or taken branches, not taken branches, but interrupts provide highly predictable serving latencies because we know when to serve and how to serve it. So it depends on your application that you are going to use. You have to be really careful of which one to use. So polling on one side ties down the CPU, interrupt efficient CPUs, multitasking. They have got priorities depending on the source that you are using and can be masked. So two examples are given. One of them is waiting for pin D2. Okay, so it will keep checking it and then it will do something else. But on the other side, you can carry on doing what you are doing. Whenever the pin D2 is 0, then automatically call the dedicated interrupt service routine to do something else. This is how important it is using an interrupt. So what we generally have is for every interrupt, there must be an interrupt service routine or interrupt handler. And when an interrupt is invoked, the microcontroller runs the interrupt service routine. And generally, in most microprocessors, every interrupt has their own fixed location in the memory that holds the address for that ISR, which we are going to talk about that in a minute. But before we get into it, I want to give you an how interrupt servicing is done or servicing interrupts are done. Now, this is the general procedure, and most of the CPUs or the microcontrollers are using these procedures. So the first thing to do, whenever you receive an interrupt, the CPU finishes any pending instructions because it cannot just stop it suddenly. So it has to finish whatever it's doing, and then it will start to serve the other interrupt. So the global interrupt enable bit is cleared, okay? And instead of fetching the new instruction, it will just hold it or save the current location of the program counter onto stack. And then what it does is CPU fetches the instruction from the interrupt vector table, which we are going to talk about it. For each ISR or each resource, there's an interrupt vector on the table, which is saved in the memory. And the instruction is usually a jump address, so it jumps directly to that address and serves the interrupt service routine or interrupt handler corresponding to the interrupt type. And when its CPU begins to execute the ISR code, the first part of the ISR typically saves the context on stack, status register, and other user register it's going to utilize to serve that interrupt routine, because we don't want to lose any data if we are just using the similar registers or same registers, if we are desperate about it. Now, before the ISR is done, the context is recovered. So we pop the save registers as well as the status register. And when we use the red eye return from interrupt, this stores back the program counter values back to the program counter, from the stack to the program counter. And the global interrupt enable bit gets set again, and we just carry on what we were doing. Okay, we are going to see an example related to this. Now, there's one thing that we need to be careful. When we are using interrupts, subroutines generally can get into another subroutine before it returns from the call. Now, the subroutines that are shared between the interrupt routines and the other programs running the microcontroller need to be re-entrant. So what is re-entrant? We have to pass simple parameters to and from the subroutines, and local variables cannot be declared through the absolute memory addresses. So it has to be done from to the stack, through the stack, because we have to use push and pop, and we have to retrieve the values or save the values in order to lose them. So if you want to write programs with re-entrant subroutines, like factorials, Fibonacci's, that they have to call themselves recursively, we need to think about utilizing stack to save the context whenever it's needed. So one of the most important interrupt or known interrupt, let's say, is the reset. So reset is a special type of interrupt that does not return to the control back to the program. So when it is resetting, you just reset the system, and it just gives you a fresh start. Okay, it resets the CPU state, registers, the program counter, and everything. So it's a special interrupt because in the normal interrupts, as you are saving the context or the program counter into the stack, then you retrieve back and you carry on. But in reset, that's not possible. So If you stuck in an infinite loop, you can use reset interrupt, or maybe there are some failures in AVR that you need to get into the reset. So power on reset is one of those. So this is depends on the supply voltage. If the supply voltage falls below the power on reset threshold, in order to protect from damage of the circuitry, it does the power on reset. We can also have external reset. So when you hold the reset pin for a couple of minutes, like in an ordinary PCs, then it will reset the whole machine. Okay, it will reset the CPU and the registers and everything. Watchdog reset is related with the watchdog timer. Whenever the watchdog timer period expires, it just resets itself. Brownout reset, similar to power on reset. The supply voltage is below the brownout reset threshold. Then the brownout detector is enabled and it just resets to reach that supply voltage level as well. JTAG AVR reset. Now, as long as there's a one logic in the reset register, one of the scan chains of the JTAG system can be used to reset. Okay, so this is one of the most used interrupt or special interrupt that we use. Now, let's get into the interrupt unit in AVR and let's understand how this AVR can create these interrupts, or the hardware around the AVR can create these interrupts. Now, interrupt unit and the global enable in SREG, there's a I, which is the most significant bit in the SREG, is the interrupt bit. So that's actually the global interrupt enable. So when you want to expect or receive an interrupt, we have to enable that bit. This is important. And if this bit is 0, no interrupt can be generated. And it is clear when an interrupt occurs, and then it is re-enabled when you use red I instruction. It will just re-enables that global interrupt enable. Okay, and if you don't do that, even if you create an interrupt or set or control the interrupt, if the global interrupt enable is not set, it's not going to generate that interrupt. Okay. Now, there are many sources of interrupts in the AVR, depending on which peripheral is incorporated into the chip. There are at least 2 interrupts set aside for each of the timers, one for overflow and other one for compare match. 3 interrupts are set aside for the external hardware interrupts. There you can put the buttons or switches over there, depending on the AVR configuration that you can have. So you can use int0, int1, int2 respectively. And you can have interrupts from the serial communication UART. So 3 interrupts from there, like one for receive, two interrupts for transmit, and SPI interrupts, analog to digital converter interrupts. So these are some kinds of interrupts that we can use to generate an interrupt. And there are a few more, which I'm going to show with the interrupt vector table. So the memories and everything which is working in harmony, interrupt unit is also has its own place in AVR. And we have got a few registers over there that we need to configure in order to expect or receive an interrupt. So let's see those registers now. The first one is external interrupt mask register. So if you want to expect an external interrupt, we have to use EIMSK, and we have to as in AVR at Mega 128, we have got external interrupt 0 to external interrupt 7 pins that you can see it over here, that we can use it for external interrupt receiving. And we also have the interrupt flag register. So when it's set to 1, when an interrupt pin changes to trigger an interrupt flag. So flag is cleared manually by writing 1. So we always clear the flags by writing 1 when an interrupt pin is deasserted. So when it starts serving it, it's deasserted. And then when you use red eye, it's just asserted again. I'm going to show you all the procedures of this step by step. And we'll see how they are going to be generated. We also have external interrupt control register A and B, sense control. So determine if the interrupt is going to be rise or full edge triggered or low level triggered. So depends on the pulse rates and so on. And we have to configure those accordingly. So interrupt control register, each subsystem with interrupt support has dedicated. They have a feature-specific local interrupt enable bits. So like the timer interrupts, they can be in the TIMSK or extended timer interrupts for timer 3. So you can find timer 0 overflow, output compare match, 0, timer 1, overflow, timer 1, output compare, timer 2, and so on. Okay, so we have to enable these accordingly depending on the resource that we use in AVR. And yet another important register is MCU control register, which we have the interrupt vector select bits. So we have got the vector table, which we can look for the interrupt service routine that we need to place on, and IV cell and IVCE. So interrupt vector select to place the interrupt vectors to the beginning of the flash, which we generally do it, or to the boot flash, and interrupt vector change. So you must need to write 1 before the IV cell if you want to change the location of the interrupt vector table. But we place it on the at the beginning of the flash memory. So like I said before, every interrupt, there is a fixed location in memory that holds the address of its ISR. And the group of memory locations set aside to hold these addresses of the ISR is called interrupt vector table. Okay, so where we have mentioned over here interrupt vectors placed at the flash starting address 0, we have this interrupt vector table that we need to use in order to serve the ISR. Now, you can see the table over here for external interrupts, interrupt 0 to interrupt 7. Then we have got timer 2, timer 1, timer 0, SPI, USART, analog to digital, EEPROMs, and timer 1 and 3, USART, and SPM, and so on. It goes like this. So you can see that the first location is reset, program address 00, and the 444 is the last one. So this interrupt vector table is allocated for address 0 to 44. So if you want to write a code into the flash, you have to start anything after the vector table if you are using interrupts. So if the program does not enable an interrupt source, the interrupt vectors are not used, and regular program code can use these locations. Okay. So if boost reset fuse is set to 0, then the interrupt vectors start at a different location depending on the boost 1 down to 0 fuse configuration. So you can change those with IV cell bits, and you can change the location of the interrupt vector, which we generally don't do that. If you have something really specific application that you need to change the place of the interrupt vector table, you do that. But otherwise, we don't prefer to do it. So How do we enable and disable the interrupts? As I already said, when we do a reset, all the interrupts are actually disabled, which are masked. Uh, so that means none will be responded by the microcontrollers if they are activated. So interrupt must be enabled or masked by the software in order to the microcontroller to respond to them. And as I already said, in the SREG status register, most significant bit, which is I, is responsible for that. So we have to enable that so that we can enable interrupts globally. And we can use a single instruction like CLI, which is clear interrupt, and we can clear the interrupt bit in that SREG. Okay. So now I'll start to give you examples related with the how AVR is dealing with these interrupts.